Hello. So in this lecture, we're going to start going through ester chemistry. So the chemistry of esters. A really nice functional group, super useful. So this is, this is a really popular functional group. It has a lot of ramifications in biology, material science, that sort of thing. So it's very prevalent. So it's nice to know some tricks about it. So we already did I just want to make note that we've done the naming of esters. So that is a functional group that I would expect us all to be comfortable with. We've also talked about some of the synthesis strategies. Namely, we did a full lecture on the Fischer esterification. And we've also talked about the reaction of alcohols with acid halides and acid anhydrides, or just anhydrides, or carboxylic acid anhydrides, that word, okay? So what I want to talk about a little bit is some esters that we haven't seen yet, and these would be lactones. So lactones are important esters. These are simply, very simply, don't make it too hard, cyclic esters. They just have a name that doesn't really sound like an ester, okay? So lactones, these are cyclic esters. Number one, these are good monomers for the synthesis of polymers. Okay, now these polymers that we make from lactones are polyesters. Okay, so polyesters look like this. We could talk about the repeat unit of polyesters. What we have is we've got an O on one side of our repeat unit, and then a carbonyl on the other side of our repeat unit. Okay, and then we have a bunch of stuff in the middle. That's a polyester. So we could have a bunch of stuff. It's awkward to put R groups. It's also awkward to define chains. Maybe a better repeat unit would be some carboxyl group attached to some carbon atom on the other side, and that's repeated, and then we have a bunch of stuff in here. Perhaps that's a better repeat unit. It's kind of hard because we could have any number of things sort of bridging the carboxyl group and the oxygen atom. Okay, so what this looks like, let's go through a specific example. Excuse me. Sorry for that yawn. Okay, an example of a polymerization. Could be, let's take a 5-membered ring with an ester oxygen, and we're going to react this with some sort of nucleophile, and this nucleophile is going to be used in small amounts, as this is just going to simply be an initiator, so a nucleophilic initiator. So we're going to take our nucleophilic initiator and add to the carbonyl carbon. This is what we've done so far with all of our carboxylic acid derivatives. We first add, that then takes our sp2 hybridized carbonyl carbon and converts it into something that's sp3. And so we call that our tetrahedral intermediate. Now the intermediate's important. This is not a long-lived species because the negative charge is going to come back down, reform the double bond, and kick out the better leaving group. So if the nucleophile gets pushed off, well, we just get our starting materials. So in this case, we're going to kick off the ester oxygen. That's going to give a nucleophile, now attached to a carbonyl. Now let's count carbons. 1, 2, 3, 4 over to the oxygen. So this is going to be carbon 1, 2, 3, 4 over to the oxygen atom. Okay, so we now have our ring opened lactone. And if you recall here, the goal is to make connect several of these together, several of these lactones together to make a polyester. What's going to happen next is that oxygen is going to be the nucleophile that then ring opens another lactone. So we can add to the carbonyl carbon, and I should see if up here, if I have addition, I should add elimination. We're going to do the exact same thing though. We're going to first add. Guess I have to draw that carbonyl carbon upside down. Oh gosh. We're now on a drawing adventure, but we still have 1, 2, 3, 4 carbon atoms. The negative charge is going to come down from our tetrahedral intermediate. Now I realize it has 2 oxygens it could push off, and maybe it seems a bit arbitrary that I'm pushing off the lactone oxygen. But recall, if we push off the other oxygen, that's pushing off our nucleophile, and we're just going back to the starting materials and not accomplishing anything. So I'm going to push off the lactone oxygen, and then I get a bigger chain. Oh gosh, 1, 2, 3, 4. And that 1 was at a carbonyl. That 4 now is at a negative charge. Now this is, this will keep adding over and over again. Whoops, what am I doing? So we keep adding, where we keep incorporating one at a time, these lactones through ring opening, and then the overall process is we have this repeat unit where we've got carbonyl carbon 1, 2, 3, 4 atoms away from our ester oxygen. Then we have this polymer structure. We call that a polyester because the thing that links the monomers together is an ester. It's not because we started with an ester. That's just helpful and kind of cute, because then we don't have to worry about, okay, is the alcohol separate? You know, the alcohol is separate from the carbonyl. Will that work? In some cases it does. But this is just an example. Okay, so when lactones are used in polymerization, as we've just saw, the process is called ring opening polymerization. So the process is called ring opening polymerization because we use the ester, the lactone, we ring open the lactone to efficiently produce our ester, which is kind of nice because we have kind of 2 sides of our chain. We've got like the tail. I'm gonna emphasize this very little. We have like the tail and the head of our unit that gets combined over and over again. And so this is using a ring opening polymerization route. It's a really nice strategy for doing head to tail polymerization, so you don't have to worry about some side reactions or as many side reactions. The other thing I want to mention about lactones really quick before we go into more general ester chemistry is the fact that lactones are often very potent medicines and biologically active agents. So lactones make for good medicinal therapeutics. Now, a prominent example is antibiotics. Now we know you probably all are aware that antibiotics certainly have some drawbacks when they're sort of abused, not abused in the traditional drug sense, but when they're overprescribed, literally overprescribed, that leads to bacterial antibiotic resistance, which is a big problem because then when we really need to use them, we can't. But we see them with both penicillin and non-penicillin antibiotics. Basically, any drug that ends with icin really mycin, is a lactone, and a lactone is a cyclic ester. It's very prominent in medicinal chemistry. I studied these when I was in grad school. A lot of interesting metabolic pathways produce really interesting lactones that can be used for a number of biological purposes. Okay, so that's enough of lactones. Let's just get into some general reactions of esters. So the first one, and so these reactions are when the ester is the starting material. The first one is just the hydrolysis of esters. And this will form carboxylic acids. Okay, so in this reaction, what we do is we take our ester, and I'm going to have the R group on the alkyl side of the molecule connected to the oxygen, maybe the alkoxy substituent, if you want to call it that, separate from the carboxyl substituent. So I'm going to have an R and an R prime. If I react that with an excessive amount of water and some H plus catalyst, I will form the carboxylic acid plus the alcohol that would result. Okay, now it's important to note that for this reaction, this is just the reverse of the Fischer esterification. It's an important mechanism, though, so I don't mind going through it, even though it might be a bit redundant, but we're taking it from the opposite approach, starting from the end. So here we have our ester intact. And the first thing that we're going to do with this mechanism, or any mechanism that involves an acid catalyst, is engage the acid. In this case, we're going to use a lone pair on the carboxy or carbonyl oxygen of our ester group. Okay, that's going to make that carbonyl oxygen more electrophilic. You could draw a resonance structure to neutralize the positive charge in the oxygen and present the carbon with a positive charge. That allows you to see that when H2O comes in, it can use its lone pair of electrons to add to the carbonyl carbon, and you could use either of these depictions. They get you the same outcome. It's just that with the first depiction, you have to draw an extra arrow to show the electrons being pushed up and onto the carbonyl oxygen. In either case, what you form is this structure here, where the oxygen that just added still has two hydrogens, so it's positively charged. We could lose one of those hydrogens, regenerate our acid, and get to an overall neutral tetrahedral intermediate. It's important to note about this tetrahedral intermediate, this is halfway to either side of the reaction. Either side meaning we could go forward and on to products, which are the carboxylic acids in this case, or we could go backwards and go back to the ester, depending on whether we have more water present or more alcohol present, because the Fischer esterification, or in reverse, the hydrolysis of esters, both of those are equilibrium processes governed by Le Chatelier's principle, which means that if we have more alcohol, we're going to push towards the carboxylic, or excuse me, if we have more alcohol present, we're going to push towards the ester side of the reaction. If we have more water, we're going to push towards the carboxylic acid side. Okay, I bring that up because it's important to recognize at this point, no matter which direction you're in, you have to know where you want to end up, right? If we're proposing a mechanism to get the carboxylic acid, let's make sure that we end with the carboxylic acid. What I'm kind of getting at is that we have 3 oxygen atoms now on this intermediate that all look very similar, except for that one at the R prime group. But in terms of like chemical reactivity, they're all fairly similar. So which one is the hydrogen going to engage? Well, it's actually going to sample all of them, but it's only the OR prime group that gets us to product, and that's what we have to account for. So we're going to put the H plus onto the OR prime oxygen. That's going to make that a good leaving group because it looks like water, looks like an H2O attached, except it's an alcohol. So we're going to let that drop off. There's a few ways you could do this, but we might as well keep things protonated for the moment. But I'm going to drop off the OR prime. Now I have a carbon with a positive charge, stabilized by resonance, certainly. You can have lone pairs come in. Whoop, I picked the wrong oxygen too. I guess I'm picking that oxygen. That's fine. Now, it's important to note that when this reaction occurred, we did lose our alcohol. So our alcohol is now taken care of. We basically have to regenerate our H plus, our proton, so that we could do subsequent reactions by this acid catalyst. So from either of these resonance depictions, you could have the hydrogen just drop off and onto the oxygen, or you could have the electrons move. Instead of from an oxygen lone pair, they could move from the oxygen-hydrogen bond. These are both just different depictions of the same molecule. That's going to give rise to the same product at the end of the day, which is our carboxylic acid, just rotated. Okay, so that's the hydrolysis. Again, it's the reverse reaction of the Fischer esterification. Now, it's important, what we should recognize is that this is under acidic conditions. So the above is an example of ester hydrolysis under acidic conditions. And they're acidic conditions because H plus was present. That begs the question, if we can do this reaction under acidic conditions, can we also do it under basic conditions? The answer is most certainly. Ester hydrolysis under basic conditions. Okay, so in basic conditions, what we use is OH minus instead of H plus. Okay, so it couldn't be more basic. It's very basic conditions. Sorry. Okay, we're going to use hydroxide instead of H plus. Now in this reaction, what we have is the nucleophilic OH minus is going to recognize an opportunity to add to our ester. And we can consider that by looking at the resonance structure with charge separation. That allows us to see that we can add to the carbonyl carbon, push the electrons up from the original depiction, or we could just add to this resonance structure if we want to redraw the structure. And in either case, we're going to get the same outcome because we're just looking at resonance structures, where we've got this tetrahedral intermediate. So this is a simple addition-elimination reaction to form a tetrahedral intermediate, as opposed to above was also an addition-elimination reaction. It's just that before we had to add, we had to make sure that our carbonyl engaged the H plus. Then we could add, and we had to lose an H plus, pick an H plus back up. Then we could eliminate, and then we neutralize. So there's a lot of like H plus scrambling in there, but it's just an H plus around an addition-elimination reaction. Okay, here we don't have to worry so much about that. So we have tetrahedral intermediate. Negative charge is going to come down and kick off the OR prime. Now, I think it's important to recognize here some Pka effects. So if you just draw this product, I mean, that sort of fails to take into account the fact that our byproduct is a strong base. And so we should deprotonate our carboxylic acid. So a preferred product under these conditions would probably be the carboxylate under the mechanism. But you could work this up and neutralize it. So we struggle with this. I guess the key is to recognize that, because just make sure the H plus is added during workup as opposed to during the actual reaction. If you add it during the reaction, you just kill it. So you're sitting around with the carboxylate until you really clean things up. Okay, but that's the basic hydrolysis. Okay, we just add some hydroxide, addition elimination, and then neutralize at the end gets us also a carboxylic acid. So like the nitrile, which is also a hydrolysis reaction, very similar mechanism in a lot of respects. Nitrile is kind of another carboxylic acid derivative. We can do two types of addition elimination depending on whether we have, acid or base present. Now, it turns out that this process, this basic hydrolysis of esters, is also called saponification. saponification. Okay, now the reason why it's called this is because this the reaction can convert esters into soaps. Okay, so it turns out that soaps, so hence saponification. Soapification, if you want to think about it that way. All right, so some background here. Turns out that animal fats better word is lipids. These are just our fats for those that haven't taken as much biology, are typically triacylglycerides. Okay, so we have tri for 3, acyl means carbonyl, and for us that's an ester right now. And glycerides, well, really, this is, let's shorten this a little bit. Glycer, that means glycerol derived. Glycerol is an important alcohol. It's 1,2,3-trihydroxypropane, or 1,2,3-propane-diol, however you want to look at it. It's just propane with hydroxy groups at each of the 3 carbon atoms. Now the ide, this is going to be an ester. Or if you have a glyceride, glycerol-derived ester. I should connect these two because IDE is also the suffix for a lot of our negative charge things. Okay, that's better. All right, so we have glycerol being recognized. Now what I want to do is draw one of these. So if you look, I've got trihydroxypropane, or propane triol. I think I said diol earlier. Propane triol, three ols. Okay, now what I want to do with the oxygens is, in all cases, I want to convert each into an ester. And on the carboxy side of these esters, I want to add a bunch of long chain groups. Okay, so I've got my glycerol in green, and I've got my 3 esters. Now, we could have a bunch of different like decorations of each of these esters, and we probably should for health reasons. What I have here are 3 saturated chains. So we call these, this would be a saturated triacylglyceride, or a saturated lipid, or a saturated fat. It's nice to have a mixed blend between these types of things and unsaturated fatty acids and fatty esters. Okay, so what you can do with this is you can treat this with OH minus and get some glycerol, sure. I'm going to just put minus glycerol over here because I don't want to pay attention to glycerol right now. But then we get, I don't care how long that chain is, we get 3 of these carboxylic, and let's go ahead and just add then H plus here. And that means I'm going to cross out this negative and just make it an OH. So this is a carboxylic acid from a lipid / fat. Okay. All right. What does this matter? Well, this then becomes, if you kind of look at these words, carboxylic acid from a lipid and fat, this then is also called a fatty acid. Fatty acids make great soaps. Why? Well, just to remind us from Organic 1, we have this kind of polar head group. And then we have this non-polar tail. Okay, this mixes with water. And we get micelles, which can trap dirt and grime. Dirt, grime, insolubles, things that don't dissolve in water. So, the problem with sort of some dirt and grease and oils, when it gets on your skin, you try to wash it off with just pure water. Nothing comes off because it doesn't dissolve in water. So what you do is you add fatty acids, which makes micelles, which can solubilize these insoluble things in water, allowing the dirt, grime, and grease to go down the drains as opposed to being on your skin. Okay, so we have fatty acid. This makes for great soaps. Now, if you look at the overall process here, we've taken animal fat, animal tissue, and we've converted it into a fatty acid. So that's why it's the saponification of fats. We convert fats into soaps. We convert kind of oils into soaps and that sort of thing. And in fact, this is how soaps were discovered. I think I've told this story before, but in some tribal areas, when they would do when they would sort of decompose of bodies, one really good way of decomposing of a body was to treat the body with lye. So lye is just a mixture of very strong bases. It burns your skin if it gets on you. Okay, and so what they found was when they decomposed the bodies in the stream using lye, which worked quite effectively, if they washed their clothes in the water, they had no idea what soap was at the time. Let's imagine this. They're about to discover it. They found that if they washed their clothes downstream of where the bodies were dealt with, their clothes were a lot cleaner. And that was because the detergents that were released from the lye decomposing the body actually washed the clothes quite effectively. And if you watch the movie Fight Club, they put this in the context of human sacrifices and actually make, in the movie, Edward Norton acts as though he gets treated with lye and you can see the burn. What's kind of interesting about that is when we talk a lot about acid burns and the issues with that, but there's also hydroxide burns you can get. If you get hydroxide on your skin, it can cause a burn if it's concentrated enough. If you get a little bit, I've gotten a little bit, like a 1 molar solution. I wouldn't recommend this, but a little bit of like 1 molar solution on my fingers, not enough to cause a burn. But if you rub your fingers together, you're like, why that feels kind of like soapy and lubricated. And the reason why is because the 1 molar sodium hydroxide was hydrolyzing the oils on the surface of my skin to form soap. So, I could just put a little sodium hydroxide in my hand, run it under the faucet, and I'll let my own body be the soap to clean myself off. Ooh, it's a little gross. But anyway, that's what's kind of happened. If you burn yourself with too strong of base, you'll turn yourself into soap soon enough, I guess. Gross again. Sorry about that. So let's finish. Let's go back to some chemistry. Let's do some reactions. Okay. So we can take esters and we can hydrolyze them back to the carboxylic acids. We can also take ester reactions with Grignard reagents. So Grignard reagents, if you treat an ester with a Grignard reagent, you do a pretty cool reaction. So let's do RO, R prime. And I'm going to mix that with a Grignard reagent. Let's pick, I guess I'm just going to do the double prime, RMGBr. Now the outcome of this reaction, after you add some H plus in the workup, is an alcohol where we have 2 double prime groups. And I'm going to do some highlighting just to emphasize this. So we have green here, then yellow here appears nowhere in the product, and then red here appears in the product twice. And so what we want to think about is that we add 2 equivalents of this, 2 moles of that for every mole of the starting material that we add. Okay, so what's the mechanism for this? We have an unusual reaction. Let's see if we can account for it with some mechanisms, and indeed we can. What it is it's a combination of an addition elimination followed by a standard run-of-the-mill Grignard reaction. Okay, so we're going to take our ester. We're going to consider a resonance structure if you'd like. We have positive charge character on the carbon atom, so we have these resonance depictions of our starting material. We're going to add to that our R double prime MgBr. And what you want to think about that as is we can take the, we can sort of think about that as R minus. I think that's helpful. R double prime minus. So that can add to the carbonyl carbon. You can use either depictions to guide your eye. Just if we use the original depiction, we have to add a second arrow, but it saves us drawing a structure. Okay, with that addition, we get to a tetrahedral intermediate. So we've done the addition step. The O minus is certainly countered by the MgBr that was used from the Grignard reagent, but I don't want to worry about that. I want to focus on the fact that the O minus wants to come back down and eliminate from this tetrahedral intermediate to form this species. And we form a ketone. Now, why do we lose the oxygen? Because breaking carbon-carbon bonds is tough. Oxygen is much better, is not a traditional leaving group, but compared to a carbon atom, we don't want to lose too many carbon atoms off of our structure. They have to be pretty special. So we'll lose the O minus, and we get a ketone. That's pretty cool. Hey, this is a great way to make ketones, right? Well, here's the issue. Ketones are actually more reactive with Grignard reagents. The way you want to approach organic reactions is generally to think about them as happening one reaction at a time, as opposed to a whole bunch. So if you just added one equivalent of the Grignard reagent, would you only get the ketone? Well, probably not, because you have to think about it as one set of reactions happening at a time. The first ester reacts with the Grignard reagent to make the ketone. And now the ketone is surrounded by a bunch of Grignard reagents. So the next Grignard reagent up has a choice. Is it going to react with the faster reacting ketone or the slower reacting ester, even though there's more ester around? So you're going to get a complicated mixture, is my point. You can't just control things by having just one equivalent of the Grignard reagent. So this is more reactive with the Grignard reagent. And this is just the Grignard reaction, which we've looked at in many contexts now. And so we're going to let another molecule of R double prime engage this species, R double prime minus, and you could consider either resonance structure. If we use this one on the right, we have to have a second arrow. If we add H plus to that, the O minus will come down, add the H plus, neutralize itself, and we get to our final product. Okay, so we can't make the ketone because the ketone is prone to doing a Grignard reaction after the fact. Is there a way to make a ketone from a carboxylic acid derivative? Let's just do a quick aside to wrap up the lecture today. Is there a way to make a ketone from a carboxylic acid derivative? Indeed, yes. Making ketones from acid chlorides. Okay, so what you do in this reaction is you take an acid chloride and you treat it with a Gilman reagent. So lithium or R2CuLi. These are all Gilman reagents. Okay, so Gilman reagents we've looked at before. They do conjugate addition over a mixture where a Grignard reaction would do a mixture of conjugate additions. These are weakly reactive. You're not going to see them engage just a parent ketone, but they will react with something as highly reactive as an acid chloride. And we'll just add, I don't think you even need H plus. I mean, you'll do H plus workup, but it's not critical for the stoichiometry, the reaction, but you'll just replace the Cl minus with an R prime. Okay. And that gets you a ketone. And what's cool about this ketone is it's got a mixed set of R groups on either side. So you can actually introduce some, you can make some molecules that lack symmetry, which are otherwise typically harder to make. Okay, I think this is a pretty cool reaction. We'll look at, we should look at one more, shoot, I forgot one reaction. I'm sorry about this. Let's look at one more reaction just so that we close out and we forgot to make amides. So we'll do this quick. Making amides. from esters. Okay, so making amides from esters. So what we do is we take our ester, sorry about this, overlook this. We're going to take our ester and we're going to react it with an amine. And the amine, we'll look at this next time, what this means, but this is secondary. And by secondary, that means there's one NH present. So what we're going to do is we're going to use that one NH to convert our ester. Help if I drew a change on this molecule into an amide or amide, depending on where you're at. The key thing, the reason why we need that NH is because we're going to form ROH. Okay. So in this reaction, if we look at the mechanism of it, we actually don't add any base to this for the most part. I mean, we can, but we can do this without base. We just have to apply some heat. So heat is necessary here. I guess the heat isn't super necessary for you to understand the mechanism. It's a simple addition elimination, but it allows us to see why this neutral nucleophile is able to add an ester, which is not as reactive as an anhydride or an acid chloride. Okay, so in this reaction, what we're going to start with is we don't have an acid or base present. So we could consider the resonance structure where we have positive charge character at the carbonyl carbon. We could add that to the secondary amine. Now, amines are basic and nucleophilic. So the lone pair could add to the carbonyl carbon. We could use either of these two depictions to show that addition, just so long as we recognize that the product of each of these, from each of these resonance structures, is the same. Okay, so we're actually neutral still because everything started neutral. And at this point, what we're going to do is see another NR2H, another amine come in and pick off the hydrogen because amines are basic. We've used them as bases before, it's just that we prefer to use tertiary amines as the base. Okay. If we do that, we neutralize our we make our tetrahedral intermediate now overall negatively charged. Turns out that the O- is more basic, but before it deprotonates, or in addition to deprotonating, what it's going to do is kick off the OR group. So the oxygen is a better leaving group than nitrogen in this case. And we see our amide get formed. Now, what about our alkoxide and our amine? Well, our alkoxide that results, the negative charge, reacts with the secondary amine that's been protonated. By picking off the hydrogen, and then we get some HOR prime, and now our secondary amine is ready to go. Okay, so that's a mechanism that I would propose to get to the amide or amide intermediate from the ester starting material. Okay, at this point, we're ready to move into the least reactive, aside from a carboxylate, the least reactive, but probably functionally most interesting carboxylic acid derivative, the amide. We'll save that, though, for next time. So until then, we'll see you later.